All right, well, welcome everybody to our set theory seminar. After the long break, we are back. And so today we have a different format than it will be the rest of the semester. We have a speaker in person here, and we also are running it on Zoom, so it's a little high-techy. But yeah, so we are really happy to have Dima Sinapova here to give her talk from Rutgers University, and she's going to speak on mutual stationarity and the failure of SCH.
Okay, thanks, Gunther. Thanks for the invitation. So yeah, I'll be talking about a result, actually two theorems. One is about mutual stationarity and the failure of SCH, and the other one will be about related to the tree property and the failure of SCH. So just qualify the title a little bit. This is all joint work with my student, Will Atkinson. Okay, so let me start with some motivation. So the motivation behind these results were like what constraints cardinal arithmetic imposes on just infinitary combinatorics, on properties of infinite objects. And when I say cardinal arithmetic, I mean the exponential function, kappa goes to the kappa. And my focus here will be singular cardinals and their successors, first successor or second successor. When it comes to cardinal arithmetic on singular cardinals, you know, the key notion is the singular cardinal hypothesis. I'll define it just for completeness in a couple of slides. But roughly speaking, this is a parallel of the continuum hypothesis for singular cardinals. And then I'm also going to relate it to this notion of mutual stationarity, which, again, the formal definition will come shortly. But roughly speaking, one can think of mutual stationarity as an analog of stationarity, but for singular cardinals. So we'll see what that means. And the third notion that I want to relate to this is the tree property, which, again, this is, if you don't know the definition off the top of your head, this is just an uncountable version of Koenig's infinity lemma. Okay, so let me start with mutual stationarity because that's probably the principle where one might know least about it. So again, what was the intuition behind it? So recall that for regular vanilla stationarity, as if we have a regular cardinal kappa and a subset S in kappa, S is stationary if it meets every club set of kappa. But one can also give like a model theoretic-esque definition of stationary sets, which is the following. Now let's take two cardinals, kappa less than lambda, kappa regular, lambda can be anything. A subset S of kappa is stationary if and only if, well, for every algebra A on lambda, there is an elementary substructure N in A, such that sub N intersection kappa is a point in S. So in terms of how this corresponds to the usual definition of stationarity, you can think of A as coding a club, so the subset of kappa, and N is the witness that this club and S intersect. All right. Okay, so for every algebra on any cardinal lambda possibly higher than kappa, we can find an elementary substructure with supremum intersection kappa in S. And this is the definition we want to think about when, in a little bit, I define this analog for stationarity for stationarity for singular cardinals called mutual stationarity. And to name drop a little bit, this was first defined by Forman and Magidor in their paper from 2000 or 2001, the non-saturation of the non-stationary ideal on P kappa lambda. And for the case when kappa is omega 1, they use this mutual stationarity to prove that the non-stationary ideal is not saturated. And then, okay, so now let me give you the definition of this mutual stationarity. So we're talking about a singular cardinal, and just for this talk, I'm going to just be focusing on the case when kappa is singular cardinals of cofinality omega. But many of these notions could be generalized for higher cofinalities. But for cofinality omega, so let kappa n less than omega be regular increasing cardinals with limit kappa. And let's take a sequence of stationary sets, an in kappa n. So informally, what I want to define is mutual stationarity to say that for any stationary sequence Sn in kappa n, and any algebra A on kappa, now kappa plays the role about lambda, there is an elementary substructure of n of A, which witnesses simultaneously that the Sns are stationary, hence the word mutual. Okay. Now, so i.e. formally, if we have a stationary sequence of sets Sn in kappa n, we call the stationary sequence mutually stationary if for every algebra A on kappa, there is an elementary substructure such that for all n, sub n intersection kappa n is in Sn. And why did I start with those A? So now let me define this principle. Mutual stationarity holds at some sequence of sets an n less than omega if every stationary sequence taken from the ans is mutually stationary. So for example, mutual stationarity holds at kappa n less than omega if simply every stationary sequence is mutually stationary. Okay, so any questions about this definition? I don't know how many people have seen it, I guess. Yeah, okay. All right. So this is mutual stationarity. Now, some history about it. So starting with a few facts that Matt and Menachem showed. So now let's take the case of the allophans. Okay? If one restricts to countable cofinality, points of countable cofinality, we have that mutual stationarity holds. So here, cof omega just denotes all alpha such that cofinality of alpha is omega. Okay, and this is just the theorem of CFC. Okay, now, so the next question is, well, what if you take cof omega 1 or omega 2? Well, it turns out, and again, this was proven by Matt and Menachem, that this does not generalize to higher cofinality. In particular, they showed that in L, there is a stationary sequence of the allophans intersection cof omega 1, which is not mutually stationary. So in L, it fails. Okay, but now, okay, so it can fail, but then the question is, well, can it hold? So this is the question they posed back in 2000. Well, can we force possibly from large cardinals that mutual stationarity holds when restricted to higher cofinalities? Okay. And now, what do we know about stationarity for higher cofinalities? So there are intermediate results between then and now. So it turns out that this will need large cardinals. Okay. Uses large cardinals and needs them. Also, just a quick note. So I made these slides a couple of months ago, when I was giving this talk for the JMM, which is a general audience, hence the italics of large cardinals. I know here everybody knows and loves them, but. All right. So, and again, this is the reason for this slide, which, I mean, I'll just, it is what it is. Yeah. Extension of ZFC, blah, 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 measurable supercompact. We are, yeah, in our proof of the theorems that I'm going to be presented, we will need a supercompact. Did I say anything about it? Okay, let's some more history. Just like a survey of results in since Matt and Menachem's paper. So why do we think that large cardinals will be essential? Well, let's go back to just kappa n's. Now, if we take the kappa n's to be supercompact cardinals, we get that right outright mutual stationarity holds at the kappa n's for any cofinality, etc. But actually, if you don't care about smaller cardinals like allophans, if you just care about a sequence having mutual stationarity, measurable is enough. This is what Cummings, Foreman, and Magider showed. And so more precisely, their theorem is that if you force with just the vanilla Prickry forcing or a measurable kappa, mutual stationarity will hold at the Prickry sequence. Okay, but now what about, the allophans? Well, by results of Kopke and Welsh, was shown that from a measurable, one can force mutual stationarity at the Aleph 2n plus 1s restricted to Kopf omega 1. So you can do it, but you have to do every other one. And again, they use like a Prickry type forcing. And also the other paper is that the hypothesis is optimal. And I actually forget which one is which, whether it was just Kopke for the optimal and Kopke for this one, maybe Arthur knows since he has a photographic memory. Okay. And so again, this question remains, what about every alaphan for higher coffinality? Before I go on, let me just make this is not really on the slides, but a quick remark. So one reason I'm talking about, we restrict ourselves to some bound coffinality as opposed to increasing coffinalities is, so this has a relation to that old open problem whether Aleph omega can be Johnson. And so, yeah, it could, and there are some recent results of Scheller putting some restrictions on what you can foresee for the mutual stationarity of the alephans if you vary the coffinalities. But I don't remember the exact statement. So, but so for yeah, so this is why here we just restrict to some bounded coffinality. And then so Omer in 2019, proved that actually yes, one can obtain mutual stationarity for the alephans restricted to Kopf omega 1 or Kopf omega k for any fixed k. And in particular, what he showed in terms of the hypothesis, so suppose you have omega many super compact cardinals, then, for any k, actually there is a forcing extension such that for every fixed k, mutual stationarity holds at alaphan intersection Kopf omega k. And by the way, I didn't mention this. Maybe I have it written later, but just in case I don't. Just as a side remark, if you're trying to prove mutual stationarity at any sequence, let's say some kappa n's, it's enough to prove it for all Rgen. Somehow it's easy to add any finite interval. And morally speaking, that goes to back to the fact that intersection of clubs is club, so to speak. But it's really important to prove it for all Rgen. So here I'm saying k less than n, but you can actually, as long as you in the proof you do it for 500 times k less than n, you get it for all n. Right. And in particular, what is the forcing? Well, it's somehow the most natural thing, one can do. So you take your super compact cardinals kappa, and then you use a full support iteration of Levi collapses to make them successors of each other. And the first one made, let's say, Aleph 2 or Aleph 2024. I mean, it doesn't matter because you just have to do it for all Rgen. Okay. And and then the bulk of the argument is to show that mutual stationarity holds. So recall from one of my facts back on the other history slide, like in the ground model, you do have mutual stationarity. Okay, so now what about the cardinal arithmetic? So in Omer's model, you have SCH. Actually, you have GCH, right? Because you're just doing Levi collapses. Holds at Aleph omega, and then him and others asked, well, what about can something like this be obtained with the failure of SCH? And so this is
you get GCH if you had it in the ground model with the super compact already.
Yes, but I think even if you don't, because you're doing call kappa n less than kappa n plus 1.
But I mean, above the supremum of the supercompacts. There's no reason you would have.
Oh, yeah. I meant GCH, you're right, a GCH up to like alpha omega. Yeah. And the next line I have is slightly inaccurate. I mean, it's a conjectural. No, it's not that it's inaccurate. It's probably completely true, but it's kind of open. This is a conjecture. Also in Ulmer's model, approachability holds at alpha omega plus 1. So this is just an old theorem of Magidor when he proved that stationary reflection holds at alpha omega plus 1 after Levy collapses. So approachability also holds. So, to the best of our knowledge, this would also, we're guessing the tree property would fail. And the reason I say, so this should be so with an asterisk, is every known model for the tree property at alpha omega plus 1 involves something called a bad scale, the argument, which is not true when you have approachability. So I should say approachability holds. So all the known ways of getting the tree property at alpha omega plus 1 would not work here. And I mean, I'm almost certain that here the tree property will fail, but this is why I wrote and so. Okay. So then there is the other question is, what about combining mutual stationarity with the tree property at alpha omega plus 1? And okay, so these are the two questions. Can we do it with failure of SCH? Can we do it with the tree property at alpha omega plus 1? Okay, and this is the definition of SCH for the JMN people. Okay, and just in case, the definition of the tree property at kappa, every tree of height kappa, levels of size less than kappa has a final branch. And know that this is an analog, countable analog of Koenig's infinity lemma, which was that any infinite finitely branching tree has an infinite branch. And okay. So yeah, Levy collapses forces SCH and actually GCH, up to the supremum of the kappa n's. And as far as we know, the failure of the tree property. Okay, so now let me state the two main theorems. Okay. So this is with Will. Suppose that we have three supercompact cardinals, so not omega many. Then we have there's a forcing extension where SCH fails at alpha omega. And for every fixed k, mutual stationarity holds at the alpha n's restricted to cofinality omega k, alpha k. So now that here in particular, we lowered the large cardinal axiom hypothesis from omega many cardinals to just three. And the other theorem is there we do need omega many. So suppose there is omega many supercompact cardinals. Then there is a forcing extension where the tree property holds at alpha omega plus 1. And for every k less than omega, again, mutual stationarity holds at the alpha n's restricted to kappa omega k. Okay, so for the next, the rest of the talk, I would like to give some sort of an idea about this theorem. So since I had in my slides, so first I'm going to be talking about just what we know about in general the strategy of obtaining this mutual stationarity, and then how we're going to combine it in each of the two cases. So if I have to just sum up this in, just like a one line, here we'll have to use some sort of a pre-forcing, and whatever strategies to get mutual stationarity has to be combined with some sort of a pre-construction because we want to force SCH to fail. And here, one will have to combine it. So let me say something about how one gets, so this is not on the slide, so I guess I was banned from using the board, so I'm just gonna talk. The way, so just some history about how one gets the tree property at alpha omega plus ones. This was first done in the 90s by Magidor Shella from a large cardinal hypothesis that now we know is more than what you need. Super compact cardinals and a huge above it. And they did some sort of a Levy collapsing of the super compacts, but using the huge above it to guess the right properties of the embedding that's to be lifted in the end, so to speak. Then later, maybe like 10, 15 years ago, myself and then Itai and then everyone else that needed to do it has been doing it by just only taking super compact cardinals. And after some point you do Levy collapses, but the cardinal that becomes omega 1 has to be chosen in a very special way. So it cannot be one of the super compact cardinals, and it cannot be the omega 1 of the ground. Somehow the cardinal that becomes omega 1 has to reflect the supremum of the super compact plus. So the omega 1 has to reflect the properties of the cardinal that's destined to become alpha omega plus 1. And that's really the reason why all those methods are incompatible with approachability. So going in Omer's model, what he does is just an iteration of Levy collapses. So we know who omega 1 is. So none of the ways one gets the tree property can work. So the key about this construction is to somehow combine this non-deterministic way of choosing omega 1 to reflect the properties of alpha omega plus 1 with the strategy of getting neutral station. Okay. All right, so the next couple of slides, any questions for this? All right, I'm going to talk about, well, what's how do we, first, how do we get neutral stationarity? Just ad hoc. Okay, so let me recall the definition. Suppose you're trying to prove it. So you have some sequence of stationary sets, Sn in alpha n. You have some algebra on alpha omega. And what you have to do is find an elementary substructure which, whose supremum intersection alpha n is in Sn for all large n. And I mean, we do the only thing one can do, right, in this situation. The idea is to build M inductively. Know that for any fixed n, just because Sn is stationary, I can find a substructure meeting it, right? So, okay, so suppose I have done this. So first, I'm at stage n and I have I already have a substructure Mn, elementary substructure of A with this property. So now the goal is to do it also for n plus 1, but without messing up the good work that we've already done. So we want to find the substructure, elementary substructure Mn plus 1, such that it witnesses Sn plus 1 is stationary. So it's a primum intersection, the given cardinal is in the set. And it end extends Mn. I mean, this is how you don't ruin the good work you've done already. Okay, now that if it ends and extends it, then it will also witness that Sn is stationary. And then again, you do the only thing you can do is take the union of the elements. Okay. So somehow the idea, and this will be in the next slide, is to formalize this inductive step. If you have a way of doing this inductive step, then you can prove neutral station. Namely, finding this substructure at n plus 1. Okay. And it turns out that then this is somewhat implicitly in Omer's paper. This is what he uses. That this inductive step can be captured in the following property, which we decided to call dagger. But the property itself is really in Omer's paper, which is the following. So for daggers of kappa states that for every stationary subset of kappa, there exists a non-stationary kappa complete omega plus 1, omega 1 plus 1 closed ideal for which S is a positive set.
Sorry, what do you mean the non-stationary ideal?
No, so let me define everything. So non-stationary means it contains all the non-stationary sets. So kappa complete is kappa complete. Omega 1 plus 1 closed means that if you take the forcing notion corresponding to this ideal, so power set of kappa mod I, this has a dense subset which is closed under sequences of length omega 1. Okay. And S is positive set means S is not in I. Okay. And also here, just for simplicity, for the purposes of the slides, I guess I'm focusing on cof omega 1, namely on getting mutual stationarity when you restrict to cof omega 1. If you want, in the proof that you can get it when you restrict to cof omega 2 or cof omega 3, etc., you need this subscript to increase. So this corresponds to the the cofinality of the points. And actually, in the paper, of course, we define dagger with two parameters, kappa and the closure. But I figured it's I mean, if one believes this, they'll believe it for them. Okay. And what Omer showed is that if you have daggers of alpha for ON, and you have either, so you need something more, GCH or approachability at each LFN. So that's not the earlier approachability I talked about, the alpha omega at each LFN. Then mutual stationarity holds at the LFNs restricted to cof omega 1. And again, it's not here, but if you have this property dagger, but for let's say omega 5 plus 1 closed ideals, then you have mutual stationarity restricted to cof omega 5 and so on. So now that this way, now we've isolated a somewhat local property. So these daggers of alpha is a property about alpha. And so that as long as we prove this local property, then we get this mutual stationarity property, which is, you know, formally about sequences of cardinals, of sets in cardinals. Okay. Oh, okay. So I do have it on the slide. Analogously, cof omega k for bigger k. Okay. And yeah, this is the key part here, that we want to reduce proving mutual stationarity to checking this as well. All right.
Okay.
Yeah.
So you have this property, this dagger.
Daggers of kappa.
For every Aleph, for Aleph 1 and also for Aleph 2 and so on at the same time, right?
Yes. Well, it's enough to show it for every large Aleph.
Right.
For Aleph and for all large n, which we're actually, when we do in our pre-reconstruction, we will be showing it for all large n.
And this is the construction of the model M that then witnesses the mutual stationarity. Is that also local like that? So in other words, I guess what I'm aiming for is how about if your sequence of stationary sets Sn is such that they come from different restrictions to cofinality. So for maybe the first one is cof omega 1, the second one is cof omega 2, and so on. Could you combine this and construct the M step by step?
Yeah, but then you need somehow, but then you need somehow daggers of kappa with, you know, the other subscript and to vary for kappa.
Right. Mm-hmm.
So the closure of the ideal corresponds to your cofinalities.
Yeah. Okay.
But of course, there are some bounds to what you can do. So and this, you know, like there's this paper of Shella that I mentioned. If you just take some fast increasing sequence of increasing your cofinalities, he found counterexamples that you cannot do it.
So that's the counterexample.
Yeah, but I forget the exact statement of it's from 2021, maybe. It's, I mean, it's Googleable, it's online.
So you don't have complete freedom.
Yeah. Okay, so we have to establish this dagger for, but also in the same paper as that Omer did the other result, he also investigates cases where you have two cardinalities, and he obtains mutual stationarity. Okay, so we want to establish this dagger, and dagger basically tells you, asserts the existence of some idea. So in the next couple of slides, let me talk about, how does one get ideals. Well, this is where large cardinals come into place. So roughly, what we're gonna use is that if L of 1 was a large cardinal in a prior life, more prosperous life, then and the forcing to get it bankrupt wasn't too destructive, then daggers of L of n still holds. So we're gonna first, I'll have a slide arguing that dagger holds when you have large cardinals, at large cardinals, and will still hold if the forcing wasn't too bad. Okay. So the warm-up is, let's get dagger at a large cardinal. Okay, so I kept the definition here because I have it. Okay, so let me go over this kind of instruction, educational fact. If kappa is 2 to the kappa supercompact, then daggers of kappa hold. So 2 to the kappa means lambda supercompact, where lambda is 2 to the kappa. Okay, so fix some stationary subset S of kappa. And we have to find this ideal. Right. Well, let's do it again. The only thing one can do. Using that kappa is supercompact, let's take an elementary embedding with critical point kappa, such that the target M is closed under 2 to the kappa length sequences. Okay. And again, what would the ideal be? Well, it would be the dual of the measure, right? So now that one can always define a measure using such an elementary embedding, well, we'll take the dual of this. So let I be the set of all x's such that kappa is not in J of x. So this I it's kappa complete because the critical point is kappa. It's non-stationary. Ideal, it's actually normal, but here we don't need it later on. But know that S may not necessarily be I positive. So in this case where we do an actual, when we actually have the right outright large cardinal, I will be the dual of a normal measure. I have an ultra field. So of course there's no reason why it will contain every stationary set field. Okay. So the next order of business is to massage this I to make sure we get an ideal where S is a positive set. Okay. How do we do that? Well, we take our S. So J of S, by elementarity, is a stationary subset of J of kappa. So, not draw a picture, but we have V here, M here, kappa is here, J of kappa is here. There is some point gamma between kappa and J of kappa, which is in J of S. Okay. And now then S is positive for this idea. Let's redefine I. Let's call it I gamma. All subsets X in kappa such that gamma is not in J of X. Now this is the desired ideal. So it's non-stationary. It's a kappa complete. S is a positive set in it. And to get that it's non-stationary, you want to make sure that when you pick this gamma has the property that it's in every J of C for all club C. And how do you get that property? Well, here you use the 2 to the kappa supercompactness, because you can enumerate all the clubs in kappa and you take the intersection of J of them. Okay, that's a club, and you take gamma in this club intersection J of S. Okay, so this is the situation if you outright have the large cardinal. I didn't say anything about the closure, but that can be a mental exercise. So here you actually, I itself is less than kappa closed, right? Because if you have less than kappa many x's, such that gamma is not in J of x, gamma would not be in the unit. All right. You need more arguments when it's a formally large cardinal, and this is what the next slide is. Okay. So how do we get a formally large cardinal? So I said recall, but what I'm, the idea is we're trying to show that if LFN was a large cardinal and the forcing to get it to its current state of being LFN was nice enough, then daggers of LFN holds. So we kind of want to repeat the argument from the last slide, but instead of an honest to God embedding, use the lifted embedding. So let J be an elementary embedding from the ground model, where LFN used to be a large cardinal, and let's call it kappa. And now suppose the forcing is, so this is what I mean by nice enough forcing. We want the forcing to be 2 to the kappa CC. We want it to be liftable using Silver's criterion, i.e. we want J of P to project to P. And in such a way that J of P mod P, the quotient, is omega 1 plus 1 closed. So you have this as a hypothesis. Also, there is a bound on the size of P, which I didn't write on the slide. But it's, Then what you do is first, you leave J to the generic extension. I'm gonna call it J again, to VG M of G star. And now we define something like the I gammas from the previous slide, but now there needs to be an extra parameter, a condition in the forcing that was necessary to do the lifting. So for every condition R in the quotient, we used to do the lifting, J of P mod G, and every gamma between kappa and J of kappa. Define the following ideals, I gamma R, very similar as before, but so we take X in kappa. Again, we want to take such that gamma is not in J of X, but now somebody has to force it. So R will force it over, VG with respect to this quotient, J of P mod G. So know that this is a definition in VG, right? Because it doesn't use a generic for JP. Okay, and here I'm the J that's here is actually the original J. So we use that, so here this technically should be a name, but I did this for the J maps. That's my excuse for it. So this definition is just in VG. Now, what kind of an ideal is this? Again, because kappa is the critical point, it's kappa complete. Principle. Now, to get it to be non-stationary and to get it to be so that S is positive, we do something similar as in the previous slide. We just have to show that we can find gamma and R such that R forces gamma is in J of S and R forces gamma to be in J of C for all clubs C. For all names for club C, right? Gamma is forced to be in J of C. And this again is done by enumerating names for clubs on the V side, taking J of that's names for clubs on the J side, take a canonical name for their intersection, argue that this has to be a club, using here the 2 to the kappa. Super compactness in the ground model, and so if it's forced to be a club, some condition forces a point in its intersection with J of S. Okay. And here one has to do a little bit more work to show that this is omega 1 plus 1 closed. But so there is, and this, I guess, originally could be found. Well, the argument that you use is essentially somewhere in Matt's chapter in the handbook, that as long as this quotient is omega 1 plus 1 closed, one can construct an embedding between the forcing corresponding to the ideal and the quotient. So the closure of the quotient gives you the closure of the forcing P of kappa mod the ideal. It's a forcing exercise. It's not completely trivial to see. Okay, any questions about this? Right. Okay. But so now what okay, what we've done here is we somehow reduced the proving mutual stationarity to checking that, you know, everyone that is a cardinal in your final extension started their life as a large cardinal, and the forcing was nice enough, namely forcing P of this property. Or everyone that was there is a cardinal in your final extension reflects a property of a kappa like this. By reflect means, I mean, because in one of our models we have a pre-cre sequence, and actually the pre-cre sequence will reflect, you know, the kappas. Okay. All right. So now let me talk about the first theorem, and I'll talk mostly about the first theorem. I won't have time to do both. So mutual stationarity and the failure of SCH. So let's fix our three supercompact cardinals, kappa less than lambda less than mu, alphabetical. And so this is just the statement of the theorem. So there's the forcing extension, but now let me give you some more details. So kappa will become aleph omega, and lambda will become aleph omega plus 1, mu will become aleph omega plus 2, and also 2 to the kappa will become mu, so equal aleph omega plus 2. Kappa will be strong limit, so in particular SCH will fail at kappa, i.e. SCH will fail at aleph omega. And, you know, we'll have mutual stationarity. And again, it's the same generic extension, which will witness mutual stationarity restricted to kappa omega k for every k. Okay, so what is the idea? Well, willy-nilly, we have to use some pre-cre forcing, right, if we're getting failure of SCH. The way what we're gonna do, as one can see here, is the idea is to take this kappa, and we want to singularize kappa, so we're gonna use the pre-cre forcing at kappa. And since we want kappa to be aleph omega, this pre-cre forcing must be interleaved with some Levy collapses in between the pre-cre sequences. So we use that. And now in the final model, we have to check that every aleph n is not technically a formerly large enough cardinal, but a reflection of a formerly large cardinal. Okay. So one can use similar arguments as in the previous slide to get dagger, and then you get what you want. Okay, so I want to I don't know how familiar, I mean, I know you're familiar, but how fresh in your mind is the pre-cre notion. So I'm actually gonna go over it so that I can talk about it as it relates to the specifics of the proof of our theorem. But yeah, this is SCH, parallel of CH for singulars. Okay, so some facts about it. It holds above strongly compact cardinal, and to violate SCH, one can use pre-cre forcing. So let me just give the definition of well, just the vanilla pre-cre here. So kappa is measurable, U is a normal measure. You know, we have these forcing conditions, finite sequences, measure one sets. Okay. Yeah, I could have just erased this. Anyway, okay, but now this is what I want to get at. So at the end, you know, we have this pre-cre sequence kappa n. This is just the union of the stems with the following kind of key property, and this is what I meant earlier when I kept saying reflection of a large cardinal. So for every, and everybody knows this, of course, for every A measure one set A, for all our giant kappa n is in A, right?
We have Matthias in the audience, by the way. Like he showed this characterization of.
Yeah, I know. Yeah, so to Matthias. Since Matthias, everybody knows. Okay, so, but in particular, what this characterization gives us is that, morally speaking, the kappa n's reflect the properties of kappa. What about the kappa n's plus? Well, they will reflect the properties of kappa plus. The kappa n double plus will reflect the properties of kappa double plus. And if you recall in our construction, we started with those three cardinals, kappa, lambda, mu, and we made them successors of each other. So the kappa n's will reflect the properties of kappa, nice large cardinal. Kappa n plus will reflect the properties of mu, another large cardinal, and kappa n double plus will reflect the properties. No, first lambda, then mu. Anyway, I have this written, I think. But yeah. So each kappa is cardinal, accessible, etc. Okay. Okay, so okay. So this is just the vanilla way of violating SCH. You start with a cardinal kappa, you blow up its power set, and then you singularize it. Okay. Now this is where I wanna. Okay, let me just talk about what our construction is, and yeah, am I really forbidden to use the portal? I mean, but I'll be also vocalizing what I'm writing. Okay, but so we have, this kappa less than lambda less than mu. So what do we do? So first, so somehow you can think of the construction in like two main steps. First, do some preparation and then the pre-pre. So pre-pre and pre-pre. This is the pre-pre. We want to force with Levy collapses to make mu equal lambda plus and also equal kappa double plus. Oh, and this should be mu here, sorry, it's a typo. So 2 to the kappa should be mu, of course. We want 2 to the kappa to be kappa double plus at Cohen subset of kappa to make 2 to the kappa equal mu. And this is just a 3-step iteration. Call kappa less than lambda, star call lambda less than mu, star at kappa mu. Okay. And then over this preparation, we have a new ground model. This will be the ground model for the pre-pre forcing with interleaved collapse. So we're using pre-pre to singularize kappa to have countable cofinality. And within the pre-pre, we're gonna interleave collapses to make kappa to be Aleph omega. So now that our collapses will be between successive pre-pre points, since we want kappa to be Aleph omega between any two given successive pre-pre points, we're only allowed to keep finitely many cardinals if we want the total to be for the type omega. And we're actually gonna keep 1, 2, 3 cardinals, meaning let kappa n be the pre-pre sequences through kappa. The interleaved collapses that we're gonna use are those co kappa n double plus less than kappa n plus 1. Okay. And then so I didn't write a definition of the forcing. Maybe I'll just say it. So the stem. So and every pre-pre forcing there's 2 parts: a stem and some measure 1 constraints. So the stem is a finite sequence of increasing sequence of ordinals through kappa, together with collapses between any successive elements of the stem. The measure 1 part is the constraint part consists of a measure 1 set, as in the vanilla pre-pre, and a constraint of how we can extend the collapses. So the measure 1 constraint for the collapses will be a function from the measure 1 set to collapses. And I didn't write this on the slide, but we are using so-called guiding generics to make sure our forcing has the chain condition. So maybe I'll just very quickly write that. Yeah. So we have like the stem, kappa 0, kappa 1, dot, 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 yeah. Kappa n minus 1, then A, C, and then here C0, C1, Cn minus 1, and now C has domain A. A is the measure one set, and for each x, C of x is an element in collapse kappa x double plus less than kappa. We don't know what the next tricky point is, but if you know that at some point you pick kappa x as, well, let me say alpha. As alpha to be your prickly point, then you're talking about a collapse alpha double plus less than kappa. And this C as an equivalence class with respect to U will be taken from, let me call GG, some appropriately chosen guiding generic, which will ensure that for any two equivalence classes, C and C prime, those guys are compatible in a measure one set. And this ensures that we have a nice chain condition at the end. So this guiding generic in particular gives you that any two conditions with the same stem are compatible. And the way one builds this guiding generic, so this is a generic for the appropriate collapse over the ultra power, but existing in V, by counting anti-chains and just by counting anti-chains and using that you have enough closure. So the number of anti-chains here will be kappa double plus, because 2 to the kappa is kappa double plus. Now, of course, if you just use a normal measure on kappa, you don't have enough closure, because the closure is only close to the sequences of length kappa. But this is where the supercompact comes into place. You actually take your normal measure U to be a projection of a normal measure on P kappa kappa double plus. And you work in that more closed ultra power in order to construct your guiding generic. And then you use the fact that the embedding map from the smaller ultra power to the more closed ultra power has high enough critical point, so that what you've constructed upstairs is still true when you just look at the ultra power by U. And for people online, I didn't write any of this down, so I am just as coherent to you guys as I am to the people in the okay. Okay, so, and then let me just mention, so with this situation, what do we have in our final model? We have our kappa becomes alpha omega, and we have some prickly sequences leading up to kappa. Let me just mention everybody who remains a cardinal. So if kappa answer the prickly sequences, the prickly points, so we keep kappa n as a cardinal, we keep kappa n plus, and we keep kappa n double plus. And then the next cardinal we keep is kappa n plus 1. So here, in the interval between kappa n double plus and kappa n plus 1, we collapse it. So in terms of now thinking ahead, we'll have to be proving dagger for everybody who remains a cardinal. There are only 3 groups that we're concerned: the prickly points, the successors of the prickly points, and the double successors of the prickly points. We have to show dagger for those 3 groups. Okay. I mean, I have it here on the slide, but it's nice to vertical line. Okay. So now, if you recall, what was the mean version of how you get dagger? Well, you get it when a cardinal used to be a large cardinal in a prior life, overforcing that wasn't too destructive. So for the first group, the kappa n's, well, they reflect the property of kappa because of, Matthias's characterization, as I mentioned earlier. And now kappa was a large cardinal, formerly large cardinal. And the first thing that we've done, I mean, what did we do? We did a couple of Levy collapses, then adding Cohen subsets. And then, of course, the prickly forcing may not be that amazing, that nice, but it can be split into various things, various portions. So, for example, to prove dagger at kappa n for a given prickly point kappa n, this is what you do. So first you take your prickly forcing and know that, so it fact, I mean, it project, you can take the finite product of collapses up to let's say kappa n double plus less than kappa n plus 1. The prickly forcing modulo of that quotient is distributive. Enough distributive that if you prove dagger in that product of collapses, dagger holds in the full extension. Because if forcing is distributive enough, it's not gonna mess what you did, what your ideal is like. Okay. Then you look at these collapses. So some initial segment of them is small enough, and then there is a separate argument that the small forcing preserves dagger. It takes a little bit of work, but a small forcing can preserve dagger. So in the end, you just end up having to show that dagger holds after forcing with collapse kappa n comma less than kappa n double plus. And to show this, now you go upstairs to kappa and you argue, well, I'm going to show that dagger holds after I force with collapse kappa less than kappa double plus. And then by the metastasis characterization for all Rn, it holds the prickly points. And now the forcing that you've done upstairs is all kind of nice forcing. So you can use this lifted embedding from some slides ago. This is in a nutshell. Okay, and with every group requires slightly different arguments, but no, just morally speaking, kappa n plus, I mean, those reflect the properties of kappa plus, which was that cardinal lambda, which was also a supercompact cardinal. So formally large cardinal, and kappa n double plus reflects the properties of mu, which again was chosen to be supercompact. At one point in the argument is settled somehow because you want to combine these, like when you talk about the kappa n plus and kappa n double plus, you have to combine both, that they reflect the properties of mu and lambda respectively, but also at kappa, successors of kappa. So at some point there is an interplay of looking at the elementary embeddings with critical point kappa and elementary embeddings with critical point mu or lambda. Yeah. But it's a delicate balance, but it works. Okay, and yeah, so forcings we use besides the prickly or collapse, levy collapses and cones, where you can lift the embeddings nicely over those. Okay. And of course, the prickly gives the failure of the SCH. So as I said, I mean, I don't let me predict it correctly. I'm not going to talk about details of the proof of the second theorem, but maybe I'll just say a little bit about it. There you start with omega many supercompact cardinals, and you somehow combine some Levy collapses to make them into the LFNs, but with this non-deterministic way of choosing what omega 1 is. And then again, you have to argue that this choice of omega 1 is still a nice enough forcing that will preserve your dagger. Okay, so let me talk, and I mean, this is the last slide with an open question. What about uncountable cofinalities? Meaning when kappa becomes of uncountable cofinality, so all of omega 1, all of omega 2. Well, so this would, of course, require some sort of a Magidor type forcing. But I think it's it's promising that something like this should work, because I think this may be due to you that there is a criterion for genericity for Magidor forcing that is similar in spirit to Matthias's criterion for pre-reinforcing. And which means that these arguments, I mean, they should have an analog in the uncountable case. Of course, there will be more complicated because for Magydar's forcing, given any prickly point, you always have to look at what I like to call the upper hemisphere and the lower hemisphere, the land above and the land below. And you may need, to be careful about your large cardinal hypothesis to get everything to cohere nicely. But I think it's, there's an ambitious grad student and wants to take on this project. It's wide open. Okay. All right, so that's it.
Thank you very much. Are there any more questions?
Have you a slide giving the references?
Yeah, so this paper is submitted. It's on my webpage.
Right.
It may also be, Will may have put it on the archive, but I personally don't really use archive. It's did you want references for the other stuff I cited, not our?
Well, more the better, because I'm out of touch.
Okay, so the main theorems, the paper is called Mutual Stationarity and Combinatorics at Aleph Omega. It's on my webpage. If you just
Right.
Google Dima Sinapova, maybe Rutgers, there's only one in Rutgers. And so Omer's paper that was very motivational for us, if you go to his webpage, Omer Ben Neria, that paper is called On Singular Stationarity Part 1. It's the one that's in advances. And there it's the relevant for the mutual stationarity at the Aleph is like section 2 and 3. And Matt and Menachem's paper, what started it all, this is called the non-saturation of the non-stationary idea on P kappa lambda. I don't know which journal that is off the top of my head. Yeah, I guess these are the names.
Question in the chat.
A comment in the chat, or Vika, could you
There is a
respond to the comment?
I
please?
posted the link to Dima's paper. Just
Oh, okay.
I see, okay.
And actually, maybe if you wait 3 days, there will be an updated because we just received and updated accordingly a referee report and are about to just fix some typos. I mean, it's nothing major, but in a few days there will be a slightly cleaner version on the website. Yeah.
Thank you.
Mm-hmm.
Okay. Any more questions or comments? I think everybody is happy.
Okay, good. I like
Thank
to
you
make
again.
that.
Thank you.
Thank you.